see how to model solar power plants and wind power plants in PSSE. So the preamble of our today's lecture, the grid connected wind farm layout, and then grid connected solar farm layout, and then power flow modeling of wind farm in PSSE, and then power flow modeling of solar farm in PSSE. Basically the data required for the modeling of solar and wind in PSSE. We will discuss in this lecture. Okay, the first one is the wind farm layout. For a wind farm layout, you can see there are different collector groups, and then which are sum up to the medium bus bar and then step up to the HV level, and then we can see that this is connected to the grid. So from here you can see that this is a 50 megawatt power plant, 50 megawatt wind farm, and each wind turbine have a size of 1.5 megawatt. So starting from this group, the first group to here, this is one collector group, and this is another collector group, and this is another collector group, and this is another collector group. So mean there are 4 collector group basically. So each one have a in each collector group there are different number of turbines. Here you can see 2, 4, 6, and 8 number of turbine in first collector group, and then 8 number of turbine in this collector group, and then 8 number of turbine in this collector group, and the remaining 9 number of turbine in this group. So basically 24, 8, 8, 8, and 24, and here. So from here 24 plus 9. So it becomes basically 33 turbines. So each have a size of 1.5 megawatt. Each have a size of 1.5 megawatt. So which make up to 50 megawatt at this bus bar, medium bus bar. So mean the these wind turbines are like WTG1, WTG2, WTG3, 4, 5, 6, and here in the same fashion with the same numbering 33 wind turbines are connected at the medium bus bar voltage. So same in the same way we can model in PSSE. First we need to have a clear idea regarding the data of this plant, like this turbine, wind turbine, the wind turbine of 1.5 megawatt generator data, and then step up transformer, and then this is one node, and similarly all turbines are connected at each node. But in PSSE we model this collector group as a one generator, like one turbine have a size of 1.5 megawatt, and 8 cross 1.5 is a 12 megawatt. So we will model 12 megawatt here, and 12 megawatt here, and 12 megawatt here, and remaining 14 megawatt here. So this will sum up to 50 megawatt, and then here you can see this is a step up transformer, and after step up transformer at the HV, that at the point of interconnection there is a switch shunt capacitor banks available to maintain the power factor at this bus also. So in this way you can see that we can now here you can see what are the information required at this time. First information is that what is the distance between from this collector group to this, mean the cable, and similarly the LV transformer, mean definitely if one transformer have a this much MVA, we will multiply this with 8 cross that MVA and model as a one transformer here and one generator here, 8 cross 1.5 like 12 megawatt, and then 12 megawatt here, and then 12 megawatt here, and then 14 megawatt here, which will step up to the HV level. So this is the modeling detail that we will do in the PSSE, detailed modeling, starting from the wind turbines data, and then cable data, and then transformer data, and then capacitor bank data, and then at the end HV bus level. That is the point of interconnection. And similarly, in order to model the solar farm in PSSE, as we know that in solar farm there are different PV strings. So PV strings which consist of different modules, series and parallel modules. So these strings are basically combined the same fashion as we have discussed in the wind is the as a collector group. Here is a PV string. So one string, another string, another string, and all these strings are connected to the inverter, and then inverter, this is known as one collector group. Basically you can say in PSSE we will model this much strings, mean, and like if there are 12 strings, so one string is modeled as a one generator. Okay, basically it is known as the one collector group. Like in wind turbine, this is known as one collector group and consists of 8 number of turbines. Here also it is after each inverter is modeled as a one collector group. Okay, and then another, and then another. All these are AC cables are connected to the at the mid MV bus. These are the blue one the DC cables, red one the AC, and then add this MV bus step up transformer to the grid, and this is the grid analyzer for basically the further control purposes. And all these are available at the point of interconnection, and the C measures basically we have to maintain the power factor at this point also. So therefore we will add the capacitor bank also. However, there is a little bit reactive power available that is basically produced by the inverter, but at the point of interconnection this much reactive power is consumed through the transformer and also through the line and then grid. So we need to provide basically the capacitor bank at the POI also. So this basically this is the structure. So first important point is that we should clear the what are the basically what is structure of the wind farm layout and the solar farm layout. So in wind farm there are a number of wind turbines are connected in a row which are known as a one collector group, and similarly there are number of collector group and then sum up to the medium kV bus bar. But what we do, each collector group model as a one generator in PSSE, and similarly we model the number of strings connected to one inverter model as a one generator in PSSE. Similar now, what are the power flow modeling data requirement for the wind farm as well as the solar farm? So the first one is that if you are modeling a wind turbine, like number of transformer, their size and their reactances are required. For 50 megawatt wind turbine, we require 2 cross 40 MVA. Why we are adding 2 cross 40 MVA? Only due to the contingency purpose. I mean, here you can see that if the fault at this transformer occurred, then due to n-1 this 40 megawatt MVA is available, so that the generation will stay in connected with the plant with the grid. So therefore, in order to maintain the n-1 contingency, we have added 2 transformer and the reactance at 12.5% at its own base, like at 40 MVA. You need to convert into 100 MVA first, then add. And then the reactive power compensation devices, how much collector cables, number of collector groups, and the voltage level, and then the cable details. Here the one aluminium cable parameters are given for 1 kilometer. We can change, basically, and get multiply with any length, and we can convert into its data. And next is the wind turbine step up transformer data. Yes, the step up from first one is the 6 LV voltage level 0.6 to 0.7 kV mostly we do, and then the reactance of transformer of MV LV is 6%. It's very low, and because the transformer, and then MVA rating is equal to or bit higher than the WTG rating FVA. So basically this transformer rated should be the greater than MVA of the WTG, so that it will not give you a signal of overloading. And then wind turbine rated a megawatt at full speed, rated MVA power factor and reactance like 0.8 per unit at own base. This is a GEW fed induction wind turbines like type 3 wind turbine. So I mean this is substation data is required, wind farm data is required, and as well as the wind turbine data is required, and transformer as well as the wind turbine alone. So this much information is required to model the wind turbine in PSSE. This is the modeling of wind in PSSE. We will do in hands-on example. Okay, next PV panels are decoupled from the grid by power converter, which is connected to the grid. So the one of the major advantage of this solar is it is modeled as a decoupled, basically a full model, that is converter model. So we will discuss there are different types of modeling, like in wind turbine modeling. There are different wind turbine, like type 1 wind turbine that is directly connected to the grid, then type 2 that is doubly fed induction with a rheostat control, and then type 3 is a doubly fed induction generation, then type 4 is a full converter model wind turbine, and similarly solar is also a full converter model wind turbine. Therefore, in power flow modeling of this solar panel in PSSE, we add its x source is equal to tetra 9. It means tetra 9 means it has a so x reactance is infinite. It means that it is decoupled from the grid. So whenever we are modeling a generator with x source is equal to tetra 9 or more than 9 tetra 9, it means that the system has a infinite reactance, that generator has a, so it means that the generator is decoupled from the grid under dynamics. So when there will be no fault contribution and there will be nothing flow of current in towards this generator. So this is the purpose of adding tetra 9. So okay, the control mode in the wind modeling wind machine we will set at control 2, because this will give Q max and Q minimum reactive power. And next is the basically modeling of like you can model up to which level, mean the it based on the information that you have. If you have information only available of megawatt, then you can directly model a generator. If you have a lot of information, you can split those information and you can make use by, as I told in the solar farm layout, we can model based on each inverter data. If we have a inverter data available, so we can basically model each inverter as a generator. So this is in this lecture we are only performing the generator modeling of a through conventional generator. We are modeling a solar, but via inverter, so we will do that is an inverter based modeling. Now latest technology, solar and generator model are power plants are modeled as a inverter modeling. So mean the now inverter based modeling is incorporated in each softwares. So we will do this is, I think this is our second last lecture, the inverter based modeling of solar and wind turbine. Okay, so this one is the only conventional model that is available in PSSE based on the conventional generator, but we have we are appending some information inside the conventional generator, and we are making this to the same as a solar generator. So the one thing is that for n lumped converter, they need to multiply m base of original converter by n. So it means if you have a data of n lumped converters, if you are modeling a single generator, then simply you need to multiply that its MVA multiplied by its n number of converter. So but it's okay, you can model in the same fashion, like in the, there are 4 collector group here, you can model as a 3 collector group, but you can say 6 collector group also. So it is based on the number of information available. If you are looking for the transient behavior, then you can model in detailed explicit modeling. However, it works. The purpose of the renewal modeling is that you can you make at least the practical realistic case, so that it will behave same accordingly as the renewable behavior have. Okay, now we are directly moving towards the wind farm and solar farm modeling. That will take a lot of time, so therefore our presentation is basically only covering the wind farm layout and the data requirement for wind and solar farm. So other than this, there are a lot of information regarding renewable power plants on websites, like how to model solar and wind. What are the difference between type 1, type 2, type 3, type 4 turbines, and then the converter modeling of a solar power plants. Yes, but here, as a planner engineer, we need to know how to model the solar generator and how to analyze the steady state and transient behavior of the solar and wind plant. So for that purpose, we should have only basic idea of the wind farm layout and the basically the data required for the modeling purpose. If you are going into details of renewable, then you can read a lot of material, but in this lecture we have covered only the basic structure. Okay, so in PSSE we will model solar and wind generator in the same single line diagram. So opening the case, network case and diagram. Okay, in diagram here you can see now we are modeling a basically solar and wind farm generator, wind plant in this case. For this purpose, the first thing is that we should add bus number, like this is called solar LV. Okay, sorry, this is bus number 1, and then solar LV. Okay, this is a generator bus, and base kV we are adding 0.6 kV. Okay, then next we are adding bus number 2, and then solar LV, and then this is bus number 3, and then solar LV. Okay, and then solar, sorry, LV4. Okay, the first one is that LV1, and this is generator bus, and this.
Tahil, you have not said solar LV2 and solar LV3 bus as generator bus.
Yes, there just for to explain why what is the effect of this bus. Okay, I just because
Okay.
when we add a generator like this, I'm adding generator at this. Okay, it's fine, mean it's connected. Now at this. Okay, now here you can see this is switched, so this shows that this bus is not a generator bus. So I have just added so I was checking that, I mean, all of you show that how to add generator on a bus. So for that purpose you need to have a always have a generator bus. Now you can see that this is switched on. Okay, and now at this bus still again should be the second bus, and then sorry, yes, now it should be now again place generator at here. Okay, and then generator at here. Okay, now one by one we will add the data. So this is basically the first collector group. All of you look at this first bus bar. This is our first collector group, and then this is our second collector group, and then this is our third collector group, and this is our fourth collector group. Now each have a different rating. So I'm modeling 50 megawatt solar, and I'm modeling 50 megawatt wind turbine, and definitely the load will be lower than this. It may be 80 megawatt or something there. So for this purpose, so I already shared with you the basically the step sheet in the previous cases in simulations file, like in, I think that was in, okay, that was in first, maybe, yes, this is. So this is a basically rough calculations sheet is available where we can find the values. But however, each generator have a capability curve. I mean, this generator can produce this much reactive power, this generator can produce this much real power. So based on the reactive capability curve, we add data inside the PSSE. However, if the information is not available, at least we to make basically you make use of little bit realistic, so we use these formulas. So what is the difference between P max? We have basically have done the P max is normally 1.05 per mean time of the original P gen, and then P minimum is the 1/3 of this P gen, and Q max using the power triangle formula. So I'm adding here 50 megawatt. You can see this is the data available at this. The P gen is 50, the P max is this, P minimum is this, Q max and Q minimum is this, and M base is this. But this is not a hard and fast rule. Each generator have a, remember, each generator have a reactive capability curves where we can use pick those values and put these values inside the generator also. So for this purpose, go to the single line diagram, single right simple right click on this network data spreadsheet, okay, and go to machine. Okay, from here you can see the P gen, the P max, then P minimum. Q gen should be placed other than here so that it will not change the parameter. So P gen, P max, P minimum, Q max, Q minimum, M base. The sequence is same. Just paste it. Sorry, that's for 50 megawatt. So we need to calculate for 12 megawatt first. Okay. Because that was the, yes, for 12 megawatt, then for 12 megawatt, then 12 megawatt, and the last one for 14 megawatt. So it means that the inverter rating have a 12 megawatt inverter, then 12 megawatt, then 14 megawatt inverter is there. So it means we are modeling only 4 inverter. Okay. So from up to this information we can model solar. So here you can see, now click on this, 12 megawatt is available, 12 megawatt P 12.6 and 4 P minimum, and then Q max is 3.9 and Q minimum minus 3.9, and the M base is this. Now the next thing is important is regarding the control of these plants. That one is the this is the control wind data. Under the wind data, it's not specifically to wind. Initially up to 33 version PSSE, it here used as wind data. Now in 34 here written as a renewable data. Okay, so we can select this control, the Q limit based on power factor and standard limit. If we are not in the 1 and 2 and 3, mostly for a solar we make use this 0.2, and but we add power factor because it will change value, the Q limits. This Q limits will be changed based on this power factor, and then we will add X source as a tetra 9. Okay, the first thing is that add data of this. It means that this is 12 megawatt inverter, and it has a MVA of 12.6 MVA, and all other P max, P minimum as the rating of inverter, and then in the control mode select this two, and then power factor should be 0.95. okay, and in the similar way make use of this tetra 9, and then it should be 2, and then it should power factor should be 0.95. okay, and similarly at this tetra 9, then it should be 2, and then power factor is 0.95. okay, and then tetra 9 and 0.95. Now in this way you have basically covered the generator modeling only up to generator point, because there is a lot of whole substation solar farm. So in the inside the layout we have a model 4 collector group, basically 4 inverter in the PSSE, for first one for 12 megawatt, and next was 12 megawatt, 12, and then 14 megawatt. So next thing is that the next is the this is the LV. So for LV next bus should be the MV bus. This okay, this is 40, we are adding 5, and bus name is MV1, and base kV is like mostly the base kV is within the range of 20 to 33 kV, so I'm adding 22 kV, and it's a non-generator bus. okay, and then MV, and then 22 kV, and then MV3, yes, and 22 kV, and then MV4, and 22 kV. Okay, set bus number 7 is here, so make it 8. okay, 22 kV. So then press escape, it will be fine. Now here you can see that there are different buses available, because mostly remember the in physical there is no bus like here you have also seen inside the diagram that there is no MV bus available up to this bus. So I mean these are the only nodes. So only one MV bus is available. There is no number of all these are the nodes. So physically these are just cables. These are the just points. So for that purpose I am making node. Simply press Control T and it will be toggled. Okay. Now here you can see that the one MV1, MV2, and then MV3, and then MV4. So these are node buses, and then between this there is a step up transformer from here to here. Okay, and then the rating of I have already told you that the rating of MVA should be the greater than this 12.6. So it means it is a 15. We are adding 13 MVA, 10 cross 13 MVA transformer with the rating of I think if it is at 10%, if it is at 13% should be the one per unit, but we can select yes, it should be 1 per unit. We are making this. Otherwise we can make it half also if it is a 6. Okay, and then for this specified X is okay. So now here you can see that we have added the initial the step up transformer, which is known as GSU. Basically this is GSU transformer. So now next thing is that we need to step up this cable, this basically cable to the direct well mean the step up high voltage transformer, then it will go to the point of coupling. So for this purpose basically we can add here we can make use of the only one bus also the cable. So I am adding here one bus that's a MV, sorry, and that is 22 kV. Okay, and here is now next, at least save our SLD so that it will save our effort. Okay, this is diagram. This is known as solar. Okay, and also we need to save the case also. Okay, now here the AC cables available in order to model the AC cable, simply add just a cable from this point to this point. Okay, the length is only 0.5 kilometer, 0.2 kilometer, and the parameters are very okay. We can add up to 1 kilometer, and we can copy these parameters from here, same parameter that we have selected. You can add here. Basically we can paste specials. Okay, can paste here. Yes, now we can copy. Okay, click on any one line and then right click and network data spreadsheet. Here RXB, put here RXB, and length because we have calculated the same. Okay, rate A is same, mean based on calculated. This is on definitely it will be 50, like 15 MVA. Okay, 15 MVA. Okay, now this is MV. We have modeled our solar plant up to MV main bus. Now the next thing is that from the layout diagram you can see there is a transformer, the step up transformer. That is here is single, but we for contingency purpose we add mostly the two transformer. The first one we have to add the HV bus, and that should be 11, and then HV, and the HV bus is 132 kV voltage level, and then we are modeling the transformer from this to okay, this should be the 40 MVA first, and then at 40 MVA at 12.5 it's 0.325, and then we are adding another 40 MVA 0.3 MVA. Okay, now here you can see that the step up transformer are also modeled. So next thing is that it should be the grid. So next is that we are adding another bus, that is POI, the same 132, and then this is point of interconnection, and then there is a transmission line from here to here, that is assume 15 kilometers on 112, and then we can see in different parameters. Okay, we can add parameters from PSSES. Like here the links is here 112. Copy these RXP and then paste here. Okay, that's fine. Now the next thing is that at POI, after POI there must be a generator. So we are adding this as a swing bus because system required at least one swing bus. Okay, so this is 100 MVA and 0, so not a wind machine. Sim. Now from here go to save the single line diagram, save the case. Almost the modeling is done. Now next thing is that go to diagram, system level default, define this voltage level 0.6. The color should, you can select any color. So I'm selecting this one and then 0.22. This color should be the, okay, this one, but make it this one and then 130. It's only for the representation purpose so that single line diagram looks fine. And then okay, now you can see, and go to diagram property font and make it 10 11. Okay, now the next thing is that you have saved your single line diagram, save your case is saved. So go back and then go to power flow solution and then solve it. So inside the, okay, here you can see that the case is met convergence tolerance. Means that system is producing this much reactive power, but look at this much real power, and this generator is absorbing. So next thing is that look at the power flow. The most important thing is that you can see that the system is, the solar power plant is absorbing reactive power. Means 0.5 megawatt is, yes, it is in range, but it the megawatt flow, the yellow one, is from swing bus towards the system bus. So what is the mean? The thing is that we need to provide the reactive power compensation with these devices, like with these plants, solar power plants or wind power plant. So now it is important that you can see the flow from real power is from solar towards the POI, but the reactive power is flowing from the swing system. So it means that the solar power plant is absorbing reactive power. So why? Because the voltage. So for that purpose, you need to increase the schedule voltage of your solar plants. So let's see what happened. So we are at, I am adding 1.02, and then why I am adding 1.02, and then 1.02, okay, and then 1.02. Now solve your case. Now can you see the reactive power flow is still is forthing to a back and mean the front and back between these. So what is the difference? The next thing is that because we have not modeled this transformer as a automatic voltage regulator, so for that purpose we need to change the tap ratio 0.95. Let's see and look at the behavior. Now it means that it's providing high reactive power. So it means we need, at least we make use of optimal tap 0.9998, so sorry, 9875. Okay, and then 9875 here, 0.9875, because PSS is not automatic software. So basically it's implement the scenario. So for that purpose we need to add data as per the scenario description. So when we give the correct scenario description to the PSSE, then PSSE will give you the correct result, otherwise it will not. So now so what you have done, you have increased the schedule voltage of your generators, and you have lowered your tap, and you will see that now reactive power will be flowing from the plant also. And also the next thing is that system still is producing 7.7 reactive power. So for that purpose, look at this value now. So mean that this generator have a maximum capability of 3. So it means it's providing only 0.6. So for this purpose, we are reducing its reactive power, tap, and let's see now the generator reactive power supplied by this generator will be increased by all these inverters basically. I mean, mostly what people do, that they just model the generator and put set their control, and they said, oh, my generator is absorbing reactive power. Definitely it will absorb, because this is a solar machines, and we have moreover we have not set any uh, tap ratio. So next, now it's seen, you can see that the reactive power produced by this is 2 point this. So it means that system is only 1 megawatt. So next 1 megawatt can be here you can see only the reactive power flow and megawatt flow is this, but only 1 megawatt is flowing here. So for that purpose we need to reduce this tap ratio. I'm adding 0.9924, so that this is a okay 0.9924. Look at the behavior now. So it means this is only now the everything is fine. See the behavior, mean the reactive power is flowing from the power plant, solar power plant, towards the grid. So it means look at this, and now you can see the system is absorbing reactive power. It means the system is maintaining the. Now the one important thing is that look at the voltage level. So voltage level is increased at this point. So for that purpose, reduce this voltage level to 1. Okay, this is 1.05, and then for this purpose the voltage level at these buses is 1.1. So mean the voltage level should be the within limit. Okay, so for that purpose we can change yes, we can change system reactive power less, and we can make 9625. Okay, 96 and then 965. Okay, 96. Solve it. Now you can see the voltage at this point is 1 per unit, and this after, it means that there is a reactive power loss, and at this bus it is 1.1 per unit. So solving the system and look at the behavior. So it means the system is producing reactive power. Right after this is a 1 megawatt, about 2 megawatt is flowing from the grid towards this. So it means that there is a compromise between this, but how we tackle this problem, like solar has a capability to provide reactive power, but this it cannot provide so much reactive power so that the system will handle. So for that purpose we need to add, like the same in we have studied the capacitor bank at HV level. So what is the size of capacitor bank? Normally we do against 50 megawatt. So what is a Q? So it means that Q max is basically 16.4. So we add 20 megawatt generator against 50 megawatt plant. So 20 megawatt capacitor bank, it means that on the system. So we need to add, mostly now we are adding capacitor bank, but switch shunt, and also SVC, and also StatCom. So now a new technology is adding with each solar power plant the StatCom. So due to the flexibility, flexibility and stability requirement. However, we are adding any switch shunt, so that you can look at the model also. So here, so we are modeling that one block step of basically 1, and then this should be 1, and this should be 10, and this should be 10. So mean 20 megawatt block. So here you can see that Now solving your case. Now look at the behavior. The reactive power is flowing from the generator towards this, and we can see that it has capacity. Okay, make use of 0.2 and then 0.2. Make it 1 and make it 1. Now solve your case. Yes. Now look at the behavior. Still, the power plant is producing reactive power at this point, but plant has not a capacity to produce so much reactive power. So it means that the reactive power should be supplied by this switch shunt, because switch shunt is a controlled of discrete, so we can add fixed shunt. Let's see, that's a 20 megawatt, so it will be basically the yes. Now you can see that this, so basically the grid is absorbing this reactive power, and also the system also plant is also absorbing reactive power, so we can make use of 10 megawatt here and see the behavior. Now you can see the system is basically, the plant is supplying reactive power, but this still there is a so this
The voltage of the bus is too high.
that's this HV bus, right?
Yes.
Yes, already is it's high, therefore we need to, we can add this we can switch it off, simple. But I want to explain that we can control this reactive power from this plant. So why it's high? Only due to the this is reactance. So if we are adding this much reactance 0.5, that we are not following the proper design, right? We are just adding data based on the calculation. So now we will see voltage is under control. Okay, when we do basically the disadvantage of PSSE is that if you are entered wrong data in PSSE, you will follow you will get the wrong result. So it will not give you any hint or any signal that you have added any wrong data. So simple. So for that purpose you need to clear regarding the information. Now you can see that the reactive power is supplying from plant to this, and the voltages are also 1 per unit, up to 1 per unit. Okay, basically that was the based on the reactance of the transformer, that was very low, and the voltages were, so it means the transformer was not accurately designed. That I initially I have added. Now you can see the voltages are fine. Okay, in this way, but make sure that the system should here you can reduce the basically the reduce the grid voltages also, like 0.9995. You will see that the more reactive power it will be absorbed by this. Now you can see everything is now under control. Solar plant is supplying reactive power to the grid. Okay, and if you will add more capacitor at this bus, like switch it on and 5 megawatt, look at the behavior. Now it's more fine. Its system is supplying the plant is supplying reactive power to the system. So in this way, now basically I'm telling that now it's okay. The system is supplying reactive power. The plant is supplying reactive power within range, that is 3.9 Q max. Look at the behavior, and then MV bus is fine, and then step up, then basically the HV bus is also fine, that 135, and look at the behavior of the grid. So in this way you can control model the solar plant in PSSE, and the same fashion wind plant is modeled. I have same added the wind data also. I have followed the wind data. Yes.
Excuse me, Mr. Tahir.
Yes.
Where is the load?
Sorry.
The load. There is no load here.
Yes, so basically I have added swing bus. So it means it's absorbing. Swing has capability to absorb. Now swing acting as a load. That is absorbing 46.9 megawatt.
Yes.
Okay.
So so
This
in
is called
POI,
this is
this is
called
a
this is
swing
called
bus, yeah.
single machine. Sorry, again repeat it.
POI number 12.
Awab, I cannot hear you well. I think there is internet problem. So repeat it again, I think.
Okay, the swing bus is POI
Yes, this POI
number
bus.
12.
Yes,
So it's absorb megawatt.
yes, it will absorb because it's absorbing megawatt as well as megawatt because it is a grid. So grid, it means that grid should absorb megawatt and megawatt from the solar. So this is your thumb rule. Otherwise, your modeling is not
Okay,
correct.
okay.
If your plant is absorbing real and reactive power, it means that you are not modeled correctly. Okay. So for that purpose, now remember that this is a single light diagram. I mean, and a solar model and same inside the system you will model the same in the same fashion. Now this is solar, and if you are if we change the name, this it will become wind. So wind have a same modeling, wind type. Only in this is under steady state. Under steady state, there is no difference between solar and wind modeling. Remember, only the difference of reactance, because in solar there is a x source of it's a decoupled. Sometime if we are modeling wind turbine as a type 3 machine is a doubly fed induction generation. For that purpose the reactance is 0.2 only. So this is difference between wind and solar, because that's a doubly fed induction generator. So induction generator has a it is a synced with the generator. So for that purpose the x source of the type 3 machine is 0.2 per unit.
The control mode will be the same
Yes,
for
control
wind.
mode will be the same because this is a renewable. Okay, wind also follow the 0.95 power factor. Okay,
Okay.
only you need to change the x source of the transformer, sorry, the generator, the collector group. And now different combinations can be generated from based on the data available. If there is a this was the 1.5 megawatt turbine data. Now you can have a 2 megawatt wind turbine. It means that you have 25 turbines total. So each have 77 like 7 megawatt, sorry, 7 number of turbines in one collector group, another 7. So in such a way, so for that purpose you need to look at the m base of each generator, and then x source and the control and pgen, so that you will you have correctly model. And in and same fashion this it will connect to the system through at this through POI, and you will see the behavior of the network. Okay. So this is what the model, how we model. This is only power flow modeling. Remember, this is modeling of solar and wind under steady state. Definitely under transient, solar have a different module, because dynamic behavior of solar is different from the wind. Okay, like wind have a sorry, in wind turbine and sorry, in wind power plant there is a wind generator, but in solar there is a panel. So dynamic model of panel is available in for solar, and similarly for wind there is a wind generator. So we will perform transient stability analysis when we will maybe it's tomorrow or the next in the next. And in that lecture I will model all generator like solar, conventional, and wind in the dynamic behavior with the dynamic fashion. And then we will perform the dynamic stability analysis, and we will see the behavior of the system. So this is how we model the power flow modeling of the wind and solar inside the PSSE. So I have share with you the detailed this layout diagram, and similarly the solar farm layout. Now it's up to you that how you basically manipulate data in PSSE and the new model. but the sequence should be the same. At least cover the LV level, MV level, then HV level, and then it should be connected with the grid. Then you will get the correct behavior of the solar and wind farm. So this is the end of our today's lecture. If you have any question, please ask regarding data, regarding solar modeling. So this uh, remember, this is only power flow modeling, mean under steady state. So under dynamic behavior, the when we create a dynamic data file for these solar and wind, that will be totally different. But in under steady state, only we can change the X source, because if it is a sometime we model this wind turbine as a type 4 machine. If we are modeling as a type 4 machine, then you don't need to worry about the X source. It should be Tetra 9, because type 4 is the converter machines based on the converters. So at least you should first check that what are the difference between type 1, type 2, type 3, type 4 wind machines. Just write on the Google Scholar, you will see different research paper based on the comparison. And also there is a comparison available in the Glover Sharma book, Power System Analysis and Design by Glover Sharma book, chapter number 6, and the first research case study is available. You will see maybe. So in this way you can model the solar and wind plant inside PSSE. So if you have question, please ask.
Okay, we have the capacitors.
Yes.
Why need capacitors?
Only we add capacitor.
Capacitor has a capability to produce. Yes.
Only to produce reactive power. Let's look at the behavior.
Yes.
If we are switching it off. Okay, first switch it on. See the behavior. 5.8 megawatt is coming from the plant towards the grid. Okay. Now I'm switching it off. See the behavior. 2.3 megawatts is going towards the grid. Okay. 2.3 megawatt. And if still if I reduce, it means that this is a maximum point. Now plant is producing maximum 3.6 megawatt under the controlled. If we change this change this reactance like 0.95 somehow, if this, now you will see the voltage boost as well as the, sorry, I've added again. No, this 3.6 is increases, I mean 3.6. I'm I mean you can increase tap, you can controlling the reactive power from the plant power side. Now see, now it's 4.7 megawatts coming towards the grid. Okay.
So we have a choice to increase the capability curve
no
or add capacitor.
Because this is the swing we have modeled. Otherwise, if in somehow if we model a dynamic load, so dynamic load always need a reactive power. Okay. So for that purpose, we need to provide the capacitor bank or other, because the solar cannot have capability to provide that much reactive power.
Yes.
So I mean basically I'm showing this behavior by changing the tap. Otherwise, if you are modeling the dynamic load inside the this here, I can we can model this dynamic load behavior here at this, but we have not started the dynamic mean part. That will be started from the next week. So I can show you now, but I'm not confusing other people that dynamic behavior of load, how this affect. Because definitely if this is a swing, just it's absorbing or producing. If we are modeling a dynamic load, then the point now system have a lot of dynamic and variant load. Okay, so for that purpose we need to provide this capacitor bank, so that it will remain stay connected with the system. Because if it here at low voltage occur less than this, it means that will be the low voltage ride through LVRT. So it means the system will not connect. So there are three things: the HVRT, high voltage ride through; LVRT, low voltage ride through; and fault ride through, FRT. So under these disturbance, the solar plants should be connected. So these are called generator compliance test: high voltage ride through, low voltage ride through, and fault ride through. Okay, so we will perform these analysis in the inverter based modeling. That is our second law lecture. I mean how to perform the fault ride through of the plant. These comes under the generator compliance test. So every generator must have passed that test: low voltage ride through, high voltage ride through, and fault ride through. If that fine, then you will set, okay, now this generator is fine, you can add. Because this is our course, I'm following the structure of course, and I'm moving forward one by one, step by step. Therefore I'm not explaining everything at this purpose. Now our purpose of today's lecture is that how to model solar and wind in PSSE only steady state. That we have achieved. Okay. Okay, now I'm leaving, and I will place this recording just within 5 to 10 minutes. And delay, sorry for the delay in the previous lecture I have placed today. Now I will place this lecture within 10 minutes.